Hi, welcome back to our lecture on a practical guide to quantitative finance interviews. Today we are going to talk about Ito's lemma, which is the last lecture about the whole stochastic process and stochastic calculus. I think Ito's lemma is one of the most important equation or formula that you should know in the mathematical in the financial mathematics, and it's actually the foundation of all the modern financial mathematics because it solves a super difficult problem. So let me first talk to you about the quadratic variation, where you can understand how important Ito's lemma is. I think the explanation on the green book is not that good because it's an interview book instead of the textbook. So today I'm going to go through all the proof and all the application of Ito's lemma so that you can understand it totally. Okay. So first, what is quadratic variation? Let's consider a random time period. Okay. Let's say from 0 to t. And within this period, there will be a separation of, let's say, 0 equal to t0, smaller than some t1, smaller than certain t2, smaller all the way to tn, which is equal to t, okay? Basically, we separate them into n different periods. And then we are going to define the quadratic variation of a function ft. Ft's qv is going to equal to, from I equal to 0 and minus 1, fti plus 1 minus fti and t squared. And basically, let's say if ft is differentiable within 0 to t, then we can actually easily find that this I fti plus 1 minus fti take the square is definitely going to be smaller than the max value of the s, where s within 0 to t, a certain period s derivative square multiplied by the max ti minus 1 minus ti multiplied by t. What does this mean? This means super complex, but let me explain it to you. It just means that if we separate this period 0 to t more and separate them into more and more smaller period, which means this maximum ti minus ti plus 1 minus ti is going to close to 0, then this quadratic variation should be bounded by 0, and it should also tend to 0. Okay, it should also tend to 0 if ft is differentiable. But the problem is, we know for Brownian motion, we have an interesting setting that this bt quadratic variation should be equal to t. Why is that the case? Because Brownian motion, we have that for any increment, right? For any increment, its variance item should be the same as its the period length with the increment length. It should be the variance of the distribution this Brownian motion is followed, right? And it's actually quite depressing or disappointing for mathematicians at the very beginning, because it means you cannot apply any classical calculus method to Brownian motion. They try really hard to find a simple and useful stochastic process, Brownian motion, but you cannot apply Taylor expansion or other kind of classical method to that. But now Ito's calculus helps that. Okay, let's see how did it goes. So let's first introduce the Brownian motion, the geometric Brownian motion. We can also call it Brownian motion with drift. So I'm also going to explain the linkage between the mathematical geometric Brownian motion and stock price. So let's define this XT as the stock price, right? But the problem is the stock price should be always larger than 0. It's always positive, right? But the return rate has both positive or negative. Okay, so we should define this as the return rate. Why this is the case? Because if we write a stochastic process as xt, which is the return rate, equal to some mu t plus sigma Brownian motion, sigma, we call this drift item, as I told you before. And this is the diffusion item, right? And if we take the derivative, we are going to find dxt is going to be mu dt plus sigma d, this Brownian motion, right? So this thing can be either positive or negative. But for stock price, it should be always larger than 0. So it's not a good model for that. So instead, we should replace the return rate so that it can be both positive or negative. Okay. And we already know this, but again, what we talked about before is that the Brownian motion is not differentiable. So how can we understand this item? How can we know the mathematical properties and all the characteristics of this dxt, right? So now we are going to start it. Let's first see how the classic calculus becomes invalid. So in classic calculus, we have df, if in classic item, okay? If in classic situation, what do you have? If we take the derivative of a function f, and this is, and we can do something like this, right? We can take the derivative according to bt, and then we apply the chain rule. We can have dbt dt here, and this is dt on the outside. But because this item is undefinable, does not exist, so this is meaningless, okay? This item is meaningless. And can we define something like df equal to something like this? Again, we still cannot do that. Why this is the case? Let's first check the Taylor expansion, okay? So for a Taylor expansion, we're actually going to have fx plus some delta x minus fx should be equal to what? Should be equal to fx delta x, right? The first derivative plus the double slash x delta x squared plus 3 factorial, which is just the 6, right? Triple slash and delta x cube. Right, we have this item. For normal functions, we do have the f for normal functions. Based on this equation, we can have df equal to d equal to f slash x dx, right? But for Brownian motion, since we have this lovely equation, I don't know if it is lovely now, because we have dbt squared, it should be equal to dt. Then the second item here, this one is no longer neglectable, okay? It is no longer neglectable because this item is not at the second order, but instead the first order. So it should not be deleted. Instead, we should keep that. So actually the ethos lemma's basic formula, which is also the first sequence, is called df of a Brownian motion should be equal to f slash bt dbt. This is actually the first item, but we should keep the second item, which is 1/2 and f double slash bt and dt. We replace this dbt square with dt, okay? So they are all at the first order. And this is proved by Ito. And now, if we replace bt with what? With the xt we have before, right? We have xt equal to mu t plus, plus sigma bt. Then what can we find? Then we can actually have df is gonna to be, let's break it down. Let's first use the Taylor expansion, which is dt plus 1/2 and the second derivative to t squared dt squared plus all the way, right? It's all the t parts plus what? Plus all the Brownian motion parts, which is xt plus 1/2 second derivatives dxt squared, right? This is dxt, this is dxt squared. And we know that dxt is equal to mu dt plus sigma dbt. So we put this in here and also this in here, and we can have this whole items to become mu square dt square plus 2 mu t sigma t dt dbt plus sigma t square dbt square, right? And we know all the items related with t can be neglected because they are just the same normal functions, okay? But for the dbt, again, it can be replaced with dt, okay? It can be replaced with dt. So it actually tends to 0 slower than other items, okay? So by keeping all that as left, we can have df equal to df dt plus mu t df dx. Okay, let's use this symbol instead. Plus the items here, 1/2, right? 1/2 sigma t square and slash square f slash square t square over dt plus 1 normal sigma 1/2 the first derivative of x with dbt, which is kept from here, and this item comes from here, this is from here, this item is from here, and this item is from the very first place, okay? So this is the final ethos lemma, and it is actually quite powerful. So we can just see the questions here. We have 2 example questions today. So the first question is that if bt is a Brownian motion and zt equals to square root t multiplied by bt, so basically it has 0, it has no drift item, right? And we have a diffusion item of square root t, right? What's the mean and variance of zt, and is zt a martingale process? So how can we define if one thing is a martingale process or not? So for a generalized linear process, it can only be a martingale process if and only if the drift item has coefficient 0. Okay. So does it have the drift item 0? We need to take the derivatives to see the property of dzt, right? And thus we can apply the Ito's lemma. So how can we do that? We have dzt will be equal to delta zt and delta bt dbt, right? Because the mu item is 0 here, and what do we left? By taking the derivatives of this item to the x, we also have a square root t. So let's start from all the beginning, okay? Let's start from all the beginning. So the first derivative of zt on bt is going to be square root t. And the first order of zt on t is going to be what? It's going to be bt, right? It is going to be bt multiplied by over square root t. And if it is the second derivative of zt square, bt square, it is going to be 0. So we just need to put all the values in that, and we can have what? We can have bt over square root t multiplied by dt plus the drift item is 0, and mu is atx is 0, and 1 over 2 and t and this item is also 0, right? Basically, we have a thing here, and we can see that before dt, we actually have the parameter bt over square root t, and this is not equal to 0 in any cases because bt can never equal to 0 if t not equal to 0, right? And hence it is not a martingale process. Okay, it is not a martingale process. And now let's go to the next question. Let Wt be a Brownian motion. Is Wt to the power of 3 a martingale process? Well, it is even simpler than the first question because we just need to define a function of Wt and t as Wt to the power of 3. Then we have what? Then f, the first derivative, by taking derivative on Wt, it is 3Wt2. And the second derivative is 6Wt. and the derivative on t, according t, is 0, right? And hence, by applying the ethos lemma, we have df wt t should be equal to what? It should be equal to zero plus 1/2 multiplied by 6 wt dt plus 3 wt squared dwt, right? Which here is just 3 wt dt. And again, for the case that wt is not equal to 0, then the drift item is not 0. Hence, it is not a martingale process. Okay, so basically, if you understand the ethos lemma, it's quite easy for you to identify if one process is a martingale or not. And that's all for today's lecture and all for today's chapter. Next time, we'll study to get more closer to the finance world. So we're going to talk about things like options, basic knowledge about option pricing, Black-Scholes models, Greeks, and option portfolios, all the things like that. So see you next time.